Okie doke, picking up where we left off, basically I was telling you what we want to do is look at some synthesis and focus in on this section of Chapter 9, which has to do with something called protecting groups. So I last left you with this nightmare scenario. Make this scary molecule. No! But actually it's not so bad. Right? If we just think about the alcohol disconnection and focus in on maybe, pushing that lone pair back and kicking that out, that just means I will use maybe my organolithium here and add it to, well, let's just show you what I have in mind. There it is. Just simple metallic chemistry, adding my nucleophilic vinyl lithium to my carbonyl. Yay! And I hope you're just like, Carpenter, you know that won't work. That's a synthetic trap. What's your problem? Yeah, it's definitely a synthetic trap, right? Because I have an acidic hydrogen there. Crud-ola. So this is simply not going to work, and I'm doomed. Well, no. Clever chemists have come up with a plan B, and that plan B is to use something called a protecting group. Basically, you temporarily mask that offensive functional group that's going to be in your way. In the case of the example we just looked at, it would be masking that alcohol. Now, in order for this to be a good idea, your protecting group should be really easy to put on in a reaction, give you a good yield, and then, similarly, when you take the darn protecting group back off again, it should be easy to take off in a high yield. So, in the example in the previous mini lecture, I was saying, well, we're not going to be able to reduce that ketone because that aldehyde is going to react first. Well, not if I protect it. Somehow block the aldehyde so that it's kind of out of the picture. Then I can go ahead and make my thioacetal, and do the reduction. So let me just make this kind of clear here. This is the protection stage. This now is carrying out the reaction I wanted to do in the first place, and then after I've done my reduction and everything's complete, I do my deprotection. So that's the strategy behind using protecting groups. Now, this chapter introduces two categories of protecting groups for alcohols and protecting groups for aldehydes and ketones. I can assure you there are protecting groups for just about any kind of functionality you can imagine. But let's start with alcohols. One of the most straightforward ways to protect alcohols is by making something called silyl ethers. So let's say I want to make this pretty hairy, scary molecule. If I'm going to focus in on this, what I'm going to do is say, well, what makes sense to look at? And I'm going to say, well, there's an alcohol there. I could use my alcohol disconnection there. Or I could do my alcohol disconnection there. And you know what? It's going to make a lot of sense to think about doing my alcohol disconnection right here, because then I can add this piece as an electrophile and make a nucleophile right there. So if I do that disconnection, it's pretty straightforward. I just basically have to go use my Grignard chemistry, and all is well. But you can see we're going to run into the exact same problem we did before. I can't make a Grignard in the presence of that acidic hydrogen on the hydroxyl group. So, again, I'm sunk. But no, I'm not sunk at all if I protect my alcohol first. So that's exactly what's happening here. My alcohol, as you know, is a good nucleophile. And if I do an SN2 step on my alcohol with this kind of funky looking halide, Well, it's a chlorosilane is what it's called. It's a silicon atom instead of a carbon. So this actually works pretty well. Silicon's bigger. You can do SN2 on chlorosilanes. In any case, what you've done is masked the alcohol by putting a silicon onto that oxygen. A silicon-oxygen bond is very strong, and this is a nice, robust functional group. What happened to the hydrogen? Well, I'll tell you what happened to the hydrogen. The hydrogen got plucked off by that nifty-grifty pyridine base. All right, so this is just an SN2 mechanism. You deprotonate the intermediate by using the pyridine in your reaction mixture. Well, now with that offensive OH bond missing, I can make my Grignard. My Grignard is perfectly stable. So after I've done my protecting group step there, I make my Grignard. Then I can add my Grignard to my aldehyde, make my all-important carbon-carbon bond, and now I can deprotect. Well, how do I deprotect? That's an interesting question. Glad you asked. I said the oxygen-silicon bond is very strong, but there's one that's even stronger, and that is the silicon fluoride bond. So by adding something like KF, or there's all kinds of different fluoride anions you can add, F minus very happily breaks the silicon-oxygen bond, and in workup you replace the hydrogen that you lost in the protection stage. So silyl ethers are very good, very popular protecting groups for alcohols. And just a quick aside, they come in all kinds of shapes and sizes, from TBDPS, TMS, TIPS, etc., etc. What these all stand for are the different alkyl groups on the protecting group. So this is triisopropyl. This is the one we just saw, trimethylsilyl. TBDPS is tert-butyl diphenylsilyl. So it doesn't matter. Let's clean this off. It doesn't matter what protecting group you use in this class. The point is that, can't write and talk at the same time here. The point is that you end up with a protected alcohol and your protonated pyridine. All right, so that is a great way to protect alcohols, and all of these, doesn't matter what the R group is, you'll use fluoride to deprotect. All right, so what this particular synthetic scheme illustrates, as did the earlier one, and I just didn't emphasize it, this is what you need to do, but it's not a great thing, and you want to try and avoid protecting groups if you can, because as you know, every reaction that you take will result in some kind of reduced yield. It's very rare to get a 100% yield in the organic chemistry laboratory. So we're going to have a deprotection and a protection step, which may go in 80% yield, may go in 90% yield. So that invariably reduces the overall yield in your synthetic scheme, which is too bad. All right, what next? Well, get back to our little example here. If we just protect that alcohol, we should be able to go ahead and make our Grignard go. All right, well, silyl ethers are but one possibility. Another possibility is to use this protecting group. This is called dihydropyran, this guy right here. And this is the product. The alcohol is clearly protected. It is a tetrahydropyranyl ether. Okay? In other words, to introduce you to the wide world of acronyms in organic chemistry, this is DHP, and this is a THP ether. So I've just protected my alcohol by adding dihydropyran under acidic conditions and made this THP ether. What I want to convey to you is that making this THP ether is a great mechanism for you to work through, both in terms of putting the tetrahydropyranyl ether on and taking the tetrahydropyranyl ether back off again. As you might expect, since this is an acetal, to deprotect, you're going to use acid and a lot of water. So hint, hint, it would be great practice for you to practice the mechanism for this reaction. All right, well, how about this? I want to reduce an ester down to the alcohol. It's chemistry we haven't learned yet, but I can tell you that a ketone is much more reactive than an ester. So if I'm going to try and do this by using something like lithium aluminum hydride, which is what you would use, it's going to reduce that down to the alcohol too. And if that's what I don't want to have happen, I'm going to have to use a protecting group. So great protecting groups are Chapter 18 chemistry, making acetals out of your ketone. Because just like the tetrahydropyranyl ether, what you can see here is this is basically an ether, right? It's a diether. And ethers are inert to anything basic or nucleophilic. So once I've made my protected ketone, once I've made my acetal, now I can add my H-. And again, this is not chemistry we know yet, but we'll learn it very soon. And now the hydride doesn't go anywhere near the acetal because it's no longer an electrophile. It goes for the ester, and yay, I get my reduced product. All you need to do is think about, well, now how do I deprotect? And you should know the answer to that question from Chapter 18. All right, okay, sometimes I want to do chemistry that has a need to protect two alcohols. In particular, how could I protect in one swell FOUP a 1,2-diol? Well, again, it's readily doable using acetal chemistry that we learned in Chapter 18. So, is this magic? Heck no. Just do a quick pseudo mechanism here. H+ protonates my carbonyl. One alcohol adds. This eventually gets turned into water. The other alcohol adds. You get your handy dandy acetal. Here is my former acetone piece, and here are my two alcohols. Again, I've made something that is completely inert to basic conditions. So if I need to do some chemistry now with the rest of the molecule that would subject it to base, I'm set. Question again, how do I go from the acetal back to my diol? All of this is a great review for Chapter 18. All right, so quick practice questions for you. How would I go from here to the alkane. I can't use NABH4 because that will only take me to the alcohol. I must use one of the reagents we learned in the previous mini lecture. Either the Wolff-Kishner or the Rainy nickel. I'm going to mix it up a little bit here. Or, I'm not going to use the name, we'll just say the Clemenson, which has the zinc amalgam. Then, well, not then, and HCl. So there you go. How would we do this? Oh boy, this is a real problem, right? Piece of cake if I think about removing that hydrogen. That will give me a great nucleophile that will synthetically get trapped immediately by ripping off that hydrogen. So if I'm going to try and do this, the first thing I'm going to have to do is protect this guy. Let's use, how about TMS, silyl chloride, and pyridine. So I get to my protected alcohol. Now I can deprotonate to get to my anion. I wonder what base I would use. Perhaps you will want to look that up in your pKa table. And I'm just going to put a little P there to say that's protected for now. And what do I add to get to that? Well, first I'm going to have to add this piece. Looks like a carbon with 2 oxygens. Oh, how about CO2? Sounds like a great idea. See how just counting your atoms can help? Add CO2, deprotect, you've made your molecule. So, there you go. That is the end of this mini lecture. It's hard. We're learning a lot of synthesis. We keep reviewing mechanism, but it could be worse. It could be so bad that I completely forgot the punchline on this joke. So that means I'll just have to look it up real quickly because I can't remember anything. And basically, how much worse could it be? Well, it's this bad. A doctor says to his patient that I have some bad news and I have worse news. So the patient says, oh my gosh, what's the bad news? Well, doctor says you only have 24 hours to live. Gosh, that's pretty horrible news. That's terrible, the patient says. How can the news possibly get any worse? And the doctor says, I've been trying to contact you since yesterday. Sick humor, I admit. See you in class.